Hello, Chemistry 12. Recall last day's lesson, we talked about the ionization of water and how water undergoes auto-ionization. And we were able to come up with a new constant called the water ionization constant. And the value of that water ionization constant is 1.00 times 10 to the negative 14 at 25 degrees Celsius. Now today, what I want to do is I want to focus on talking about acid ionization constant. Now, one thing for you to be aware of is that for strong acids, the concentration of H3O plus is equal to the concentration of the acid because the acid dissociates completely in water. So let's say we had HNO3. So if we have HNO3 with water, because it's a strong acid, it dissociates completely to form H3O plus and NO3 minus 1. So if we had a concentration here of 1.5 molarity, concentration of H3O plus would also be 1.5 molarity. Concentration of nitrate would be also 1.5 molarity because of the fact that it's a 1-to-1-to-1 ratio. So the concentration of H3O plus is usually equal to the concentration of the acid. And this has to be for monoprotic acid. One thing you need to be aware of, and I want to make a note of it here, is that the definition of H3O plus is not the same as the definition of the acid. Okay, so please be aware of this. The definition of H3O plus is not the same as the definition of the acid. Definition of the acid is what is the substance that actually donates the proton, while the definition of H3O plus is the chemical that's a result of that donation. Okay, for weak acids, the acids do not dissociate completely. And as a result, equilibrium system exists, not exits. In other words, the concentration of the acid does not equal the concentration of H3O plus. Now, let's say, for example, HF, which is a weak acid. So we have HF plus water. Because it's in equilibrium with H3O plus and F minus 1, let's say we start off with 1.5 molarity of HF. Concentration of H3O plus, we don't know. Concentration of F minus 1, we don't know, because the equation does not dissociate completely. So to calculate the H3O plus for weak acids, we need a new constant. So again, since this is equilibrium, we have KEQ is equal to the concentration of H3O plus, concentration of F minus 1, all over concentration of H2O, concentration of HF. Now, again, since the water is a constant concentration and it's pure water, what we can do is we can merge it into the KEQ here. So KEQ is equal to the concentration of H2O, which is equal to the concentration of H3O plus, concentration of F minus 1, all over concentration of HF. And since we're talking about a weak acid dissociating to form ions, this combination, we call this Ka. or the acid ionization constant. Okay. Now, so Ka is basically the concentrations of the ions of a weak acid divided by the concentration of the acid itself. Okay? Now, a couple of things for you to be aware of. Ka values are generally for solutions that are less than or equal to 0.1 molarity. Notice we kept the HF concentration in the equation. So for weak acids, there's enough unreacted acid molecules present at equilibrium. Therefore, the concentration of the acid must be included in the Ka expression. The larger the Ka, that means more H3O plus is produced at equilibrium, and the acid is considered to be stronger. Now, why? Because remember, again, for this one, you could think of it. Stronger acid what does that mean? It means more dissociation. The more the dissociation, what that means is more ions. And if you have more ions, what happens is you have a higher K value. In this case, Ka. So if you were to take a look at the acid-base chart here, you will notice the stronger the acid, as you go up the left-hand side, as you go from weak all the way to, let's say, iodic, notice the value on the right-hand side actually goes up, okay? So the stronger the acid means that more dissociation means more ions means that there's a higher Ka value, okay? So they are directly proportional. Now, notice for strong acids, they don't have a Ka value. Okay, the question is why? Okay, it's a mathematical reason, so I'm just going to leave that for you, and I want you to try to figure out why is it for strong acids, why are there no Ka values? Why is it just very large? Okay, now what we're going to do is I want to go over a few examples on how we can approach a question like using the Ka values. Okay, so I want to go over a couple of questions. So right here, you have this particular worksheet. I want to go over question number, let's say, I don't know, let's say 1B. Okay, so let's go over 1B, and let's go over 1E. Okay, so for question number 1B, it says calculate the H plus and OH minus 1 in the following solutions. Now, so for question number 1B, the first step that you need to do is go, okay, HNO3. Is HNO3 strong or weak? In this particular case, you look at the chart, and if you take a look at the chart, you will see that HNO3 is a strong acid. So what does that mean? It means that it will dissociate completely. So if we looked at the homework here, okay, so it is a strong acid. So dissociate completely. Because it dissociates completely, so therefore the concentration of H3O plus would be equal to 0.50 molarity. Okay? Now, so if you look at the answer, that's how you get 1B down in the bottom left here of 0.5. Now, how did they get the answer of OH minus 1 is 2.0 times 10 to the negative 14? Well, since we're asking for OH, we have to go to KW is equal to concentration of H3O plus times concentration of OH minus 1. And I'm just running out of space here, so this would be 1.00 times 10 to the negative 14 is equal to 0.50 times concentration of OH minus 1. Okay? So that's how we would calculate something like 1B. Now, it's pretty straightforward. But what we do is for 1E, we do the exact same process. So for 1E, what is it? It's 1.0 molarity HCN. We do the same thought process. So 1.0 molarity HCN. Now, again, is HCN strong or weak? You take a look, if you look at your acid-base chart, wherever that is, where's my acid-base chart? Okay. HCN is on the left-hand side. That's the acid. And if we look for it, it's right here. HCN. Now, notice it's an equilibrium. So what we have to do is if we look at here, HCN, this is a weak acid. Therefore, equilibrium. So how do we approach this? So we go, okay, HCN, you can add water here, is in equilibrium with H3O plus and CN minus 1. Hey, we have to do calculations. What do you remember doing? Of course, ice tables. Okay, and the same setup. Ice, but we don't have to fill in water. So this will be 1.0 molarity. This would be 0, 0. Now, again, going back to equilibrium, you know, this would be minus, this would be plus, this would be plus, X, X, X. Again, goes back to ice tables, mole ratio, and you know the products went up because they started with 0. So here would be 1.0 minus X. This would be X. This would be X. Again, we have our equilibrium concentrations. So we go, okay, Ka is equal to concentration of H3O plus, concentration of Cn minus 1, all over concentration of HCN. So looking at the acid-base chart, we can find out what our HCN value is, which is 4.9 times 10 to the negative 10. Okay. So here is 4.9 times 10 to the negative 10 is equal to X squared all over 1.0 minus X. Now, you can do quadratic, Okay, for those of you planning to take AP, you should know how to solve this equation using quadratic. But for regular Chem 12, what you can rest assured is this minus x, you can ignore. So then what you have is 4.9 times 10 to the negative 10 is equal to x squared over 1.0. And solving for x, what you have is x is equal to the square root. So square root of 4.8 square root of 4.9 e negative 10. And you get 2.21 times 10 to the negative 5 molarity. And that is the concentration of H3O plus, because that is what you're solving for. All right, now, then what you can do is, I want OH minus 1, so you go, okay, Kw is equal to concentration of H3O plus, concentration of OH minus 1. So that's 1.00 times 10 to the negative 14 is equal to 2.21 times 10 to the negative 5 times the concentration of OH. Solving for OH minus 1. Okay. You get 4.52 times 10 to the negative 10. All right. Now, you might say, wow, that was a lot. Not really. The second part of this question was exactly the same as the second part of the first equation, of the first question we did. The only difference was the first question seemed easier because we did not have to use ice tables to find H3O plus. Because the first question, 1b, was basically a strong acid, it dissociated completely. It was easy to figure out the H3O plus. For a weak acid like HCN, it was actually a little bit more involved. But the whole idea is exactly the same. You're still trying to find the H3O plus. Okay? Now, let's take a look at question number 2. I'm going to start off with question number 2. I'm going to look at question number 2b. Okay? Now, it says, given the following H3O plus or OH minus 1 and the acid concentration of the solution, calculate the dissociation constant Ka. Now, the first question is this a weak acid or a strong acid? Okay, since they give us the acid concentration. Now, this acid is a weak acid. Why? 2 reasons. Number 1, you're asked to calculate the dissociation constant, Ka. Recall, Ka is only applies to weak acids or something in equilibrium. The other thing is this, take a look at the concentration of H3O plus. Take a look at the concentration of the acid. Notice they are not the same. In this case, the H3O plus concentration is much less than the concentration of the acid. That's another indicator of a weak acid. Because if it was a strong acid, remember, strong acid, the H3O plus must equal the concentration of the acid. Okay? In this example, because the H3O plus is less, it's a weak acid. So, how do we approach this? So for question number 2b, we set it up. Because it's a weak acid, we have to set up our ice tables. So we have HA plus H2O is in equilibrium with H3O plus and A minus 1. So again, we set up our ice tables. Okay. The question is, where do we put in the numbers? Well, they gave you the concentration of 3.5. So that is the acid concentration. So here we start off with 3.5. Now, Mr. Chan, where do you put this 4.2 times 10 to the negative 5? Where do you put that? The 4.2 times 10 to the negative 5 is at equilibrium. Whenever they give you the concentration of H3O plus for a weak acid or a weak base, it is after dissociation, after it reaches equilibrium. So here you start off with 0. This is minus, plus, setting up the same ice tables. This would be 4.2 times 10 to the negative 5, 4.2 times 10 to the negative 5, and then 4.2 times 10 to the negative 5. And here, if we do the subtraction, 3.5 minus 4.2e negative 5, this would be like 3.49996. Now, some of you might say, well, Mr. Chan, isn't that just 3.5? The answer is yes. And so this goes back to when we were doing our calculations. Remember, I could ignore the x. So here, because the change is so small, we don't have to worry too much about it. So you just plug it in. Ka is equal to concentration of H3O plus, concentration of A minus 1, all over concentration of HA. So what you have is, in this case, it's 4.2 times 10 to the negative 5, all squared, over 3.49996. And so I get an answer of 5.04 times 10 to the negative 10. Okay, so hopefully that is pretty straightforward. Okay. Now, one thing for you to be aware of is notice E, F, G, and H. Same type of questions, but notice they gave you OH minus 1. So it seemed kind of, contradictory that you are given OH minus 1 when you're asked for the acid concentration, when you're given the acid concentration in the question. So how can you rectify the situation? So here you can use Kw to find the concentration of H3O plus. Once you do that, then everything else looks very similar to the question we had down here. All right. All right, ladies and gentlemen, thank you very much. Have a good day. Bye-bye.